Starting from me, I'm Paolo Rudatis, I'm 34 years old, I'm Italian from Ferrara province, which is belonging to the Emilia-Romagna region. I'm a chemistry researcher, graduated with PhD from the Vienna University of Technology, and I am a particularly curious human being. Hence, I have many passions, both work-wise and as hobbies. As a researcher, in particular, I enjoy electrochemistry, photochemistry, materials and thin film deposition, as well as device engineering, scientific instrumentation, and analysis, physical, chemical analysis. Well, if I think of it, my scientific journey starts really early when I was about to turn 14, when the first seed was planted and somehow the first vision was conceived. While I early realized how dramatic the climate situation was, my grandfather inspired me by the same topic, lent me a Jeremy Rifkin's book titled The Hydrogen Economy. After each page, I was getting more and more convinced I want to be a chemist because I want to fully understand the science behind the green hydrogen production, so to enable an efficient production of it. Now, much has changed since then, but what still has not is my motivation to play a role in the energy sustainability. My first research group at the University of Ferrara was particularly committed in bringing forward green energy and fuels projects. Therefore, not only I had these preferences, but those found fertile ground. I gained my bachelor's in 2013 with a review thesis on dye-sensitized solar cells, and 2016 my master's with an experimental thesis about hematite thin films for oxygen evolution reaction, OER, the notorious bottleneck half reaction of water electrolysis towards green hydrogen. From there, I started my PhD at the Vienna University of Technology, working initially on graphene oxide sensors, then later continuing my work on co-doped oxide thin films for oxygen evolution reaction. The PhD journey was challenging, more than expected, also due to the COVID pandemic, but after graduating and another short school teaching experience in Italy, I landed again at the University of Ferrara as a postdoc, this time motivated by an extremely ambitious EU-funded project on CO2 electrochemical reduction, so CO2 valorization. The project was called SOREC2 or SOREC2. This aimed at prototyping a standalone photochemical cell converting CO2 into value-added products, namely ethylene and ethanol. My contract lasted 2 years and ended just before seeing the prototype full assembled. I was anyway satisfied with my contribution and what I could learn from this enriching experience. Since then, I'm looking for new opportunities. Well, the synergies that I see between these two research areas in the context of the energy transition would be probably three main ones. First, the energy transition synergy itself, which is based on the principle of abating CO2 emissions and fine dusts. There, it is crucial to create diversified pathways to store green energy chemically. Second, the technology itself, which is based in both cases on sunlight absorption, electrochemistry, electrochemical cell, and the fabrication of electrodes, controlled to the nanoscale. Third and last synergy, the need to work in continuous, which may be something trivial for some people, but in terms of technology and setup, it changes greatly, intensifying challenges. Well, the opportunities and challenges that I see here in the seawater-based hydrogen production, many in both cases. So if I talk about the opportunities, I see first the fact that the most important resources of our time, namely fresh water, is spared. Furthermore, in detail, there are few ones, so there's no desalination required, skipping the costly and energy-intensive desalination step. This consequently, as a second point, reduces the capital cost for the infrastructure. The seawater acts already as a natural electrolyte. Also, electrolysis can be paired conveniently with offshore wind and solar power. And also let me add like two last points. The fact that, as I was talking about before, the freshwater spare, this is particularly important in water scarce regions, so that are actually by the sea, so coastal. And finally, the recent breakthroughs that occurred researching new catalysts have improved a lot and improved the ability to carry out direct seawater electrolysis, approaching targets such as durability and large-scale operations. The challenges that I see also multiple, as I was saying. I can mention a few: the corrosion of all electrochemical components, the toxicity of the evolved chlorine, also highly corrosive, the formation of hydroxides of sodium and calcium that can even cover fully the electrodes, stopping the operation. The higher cell voltages to overcome low electrical conductivity still is not low, but somehow with so many things, somehow pollutants or contaminants is considered low. And the kinetics of the side reactions as well. So utilizing energy that we would need only for the hydrogen production. And other impurities, for example, organic compounds, microorganisms, sediments that can cause biological fouling and damage a catalyst over time. And finally, also the discharge of the brine into the ocean. So we can maybe make salt out of it, so sodium chloride, and use it, for like table salt. But if we discharge it directly into the ocean, that could also damage local marine ecosystem. The role that the youth can play in accelerating, boosting the innovation and the adoption of green hydrogen technologies surely is a major one, especially if well organized and structured. We have built our academic and scientific knowledge fully surrounded and involved in these kinds of projects, and we have the enthusiasm and the ambition to see them come true. Unfortunately, I must currently observe a shrinkage of the opportunities in the field. Here I believe to be a perfect example, as I saw with my own eyes, European companies, even renowned ones in the field, forced to close. And myself, after CO2 valorization postdoc, looking for a new job for almost a year now. A generation of experts know the current times do not look so promising for investing on energy transition systems with low TRLs, which means technology readiness levels, very important for market and so on. So without the economical growth, because these fundings, slow down, and also people like during war and bombed human beings are more concerned in the new renewable solutions. Yet the complexity of the situation also seems to show a bright side, if we can call it this way, of course. People are confronted with highest prices of fuels right now, and who installed their own solar panels and wind turbines are saving much more money, so making renewables now even more advantageous than usual. The advice that I would give to early career scientists could be: call me, let's talk, and eventually do something together. And maybe slightly more serious, the more we are, the better. We can do something great for the energy sustainability, and we are already now with this interview, the crucial communication, and of course with the overall HySEas project, the SOREC2 project I worked in, and also another project that I know from my previous university, Condor. Also SOREC2 project and Condor were two projects funded by EU. I can also add, as for all visions, it is going to be, not easy. It's going to be an adventure, basically. There will be obstacles. I've already seen them. I already overcome them. Some of them not. Maybe, went around. But this is why we start, and you will start your pathway. And if it was a known one, you wouldn't have chosen it. So I also admit I'm still sincerely enjoying where this pathway has led me so far. So please join us. I would be happy to contribute in all possible ways to the project and to a faster energy transition. So I even applied practically and scientifically to contribute to HySEas. So let's see where this is ended up.